In a couple of previous videos, we imported some ticker data from Yahoo Finance and then separately imported inflation data from the Bureau of Labor Statistics. In this video, we're going to do a bit of plotting and graphing to see where we can see relationships among the data. Everything's the same except one thing. I decided in the Yahoo Finance data, I added one more ticker, which is Bitcoin. I'm just curious how the correlation comes with inflation and everything else. And just a reminder on what we did, we are looking at the monthly change. In other words, the change of the adjusted close month by month for each of these tickers. We use the pct_change function in Python because it's looking at the change from one month to another. Now this first column is has null data in it. So we'll start by cleaning up the data. We currently have 65 rows. We'll drop the NA columns, or the NA values. 63 rows, so we only lost 2 rows that had null data. Now let's plot it. So we'll start by creating our plot. We say we want a legend. We give it the title monthly %change, the ylabel %change, and the xlabel year. And then give it a few line widths. Linestyle dash means it's effectively a solid line. And then we show. So inflation is the one here that's really a bit of an outlier. We see a lot of the other stocks tend to be kind of clustered together down here. So we might want to take a bit of a closer look. One option is to reduce the number of columns in this data frame so we can look at a smaller subgrouping of stocks. Another option would be to do something like a correlation matrix. So say monthly change core. That will give us an idea of the correlation across each of these. So 1 indicates a positive correlation, which means, in other words, they tend to move in lockstep. A 0 means no correlation, and a -1 means absolute negative correlation, where they go in reverse of each other. Now, that's a range, right? So something that's maybe a 0.8 or 0.9 is highly correlated, highly positively correlated. They're not perfectly correlated. Something that's minus 0.8, minus 0.9 means highly negatively correlated. So these are important when we're doing any kind of supervised or unsupervised learning. If we're thinking of supervised learning like regression analysis, a lot of times we want to pick features that are correlated with the target that we're trying to predict. But we also don't want to pick features that are highly correlated with each other because that causes a bit of confusion in the model. So, the example I've given before, an easy example is transmission, automatic or transmission manual. We can typically compute one from the other. So if it's not a manual, it's probably an automatic. So that's where we might have big correlation within a group. Nonetheless, the correlation numbers can be interesting to look at. If we look for highly correlated items, we see probably Microsoft and Apple. You see their stock price has a 0.7. It's not a perfect correlation, but a pretty good correlation there. Microsoft and Amazon as well, a fairly good positive correlation. If we take a look at Microsoft and say KeyBank, a low positive correlation. Microsoft and AT&T, again, low positive correlation, but those are different types of stocks. Microsoft is a growth stock that happens to pay a dividend, where the regional banks like KeyBank, Huntington Bank, and the telecom providers like AT&T and Verizon tend to pay out more in dividends, but not necessarily have a whole lot of stock price appreciation. As a matter of fact, if we take a look at the correlation between, say, Verizon and AT&T, we see it's fairly strong at 0.62. Not a big surprise there. If we look at the correlation between Verizon and Huntington Bank or KeyBank, a slight positive correlation. But these are all numbers, and perhaps it's a little bit easier if we look at this in a correlation matrix graph where we can use colors. So I have a little snippet I'm going to throw in here. We're basically going to save what I just showed you into a variable called matrix. And then we're going to plot this using shades of green to show correlation. And then we will grab a few variables that we're going to pull out, and we're going to use those variables to show our X and Y labels. And let's take a look at what this creates for us. Okay, so this is a bit more appealing to me because we can take a quick glance. Green means a very strong correlation. So the darker the green, the stronger the correlation. White means either negative correlation or weak correlation. So one thing we'll notice right off the bat, Huntington Bank and Key Bank, both regional banks that serve the Midwest, very strongly correlated. You see very dark between the H band and the key. As a matter of fact, let's take a look at, see what the actual numbers are there. From Huntington Bank to Key Bank, 0.9 correlation, very strong correlation among the regional banks. AT&T and Verizon, once again, you see a fairly dark green there, so highly correlated there. But then we look at ones that aren't very correlated. So AT&T and Amazon. Neither pay a dividend. AT&T pays a big dividend. Amazon pays no dividend. Amazon more focused on stock price appreciation, where AT&T focused on the dividend payout. So not a lot of correlation there. Microsoft, we see Apple, Amazon, and Google to some degree are highly correlated. Meta, highly correlated. NVIDIA, highly correlated. But now we also notice some things that are not correlated. KeyBank and Lilly. Not very correlated. Lilly's had a hell of a good stock run in the last few years, where the regional banks are doing what regional banks do and stay fairly stable. The other one that we'll notice has a negative correlation is inflation. And what's interesting is the correlation of inflation versus the different ticker symbols. A lot of times when inflation goes up, tech stocks get hurt because a lot of their earnings potential is in the future. So it's assumed they're going to make maybe $1 billion in 5 years, but if the rate of inflation goes up, that $1 billion is worth less in current terms. So that's why they tend to get hit. I think it's also interesting to take a look at inflation in Bitcoin. Bitcoin's often considered an inflation hedge, but we actually see here that that inflation and Bitcoin appears to be somewhat negatively correlated. Let's see what we see here. Sure enough, negative correlation. But then again, inflation is negatively correlated with almost every asset class. It's just interesting that Bitcoin is there with about the same correlation to inflation as Huntington Bank. And banks don't tend to like inflation much because that tends to push up interest rates, which means fewer people will qualify for a loan. So banks and inflation tend to run opposite. But one consideration that I had on this, while I like looking at the correlation of inflation and other asset classes, I almost want to shift inflation 1 or 2 months later, because what stocks tend to react to is inflation news, and that tends to lag. We don't tend to know February's inflation until much later in March, and then stocks react. So I think that might set off these numbers a little bit, where I'm almost tempted to shift the inflation numbers by 1 or 2 months to reflect when we know what the inflation rate is versus the time that inflation actually happened. Now, one final graph we can look at that's really handy is this concept of a scatter matrix. So I've pasted in a little code snippet here where we're going to take a look at our correlation values again. And we are going to take a look at a matrix where we look at one variable versus another. This can be a bit of a busy diagram, but a very helpful one nonetheless when we're analyzing our data. So this creates this graph. And in this graph, we're comparing a lot of information. We see we have ticker symbols here on the left and inflation, ticker symbols here on the bottom and inflation. And then each of these boxes is plotting the monthly change of that intersection. So the monthly change of Apple and inflation together here gives us this graph. Now, it's not a bad idea to maybe reduce the number of things we're plotting here, because this gets to the point where we can't really see it. So we might want to zoom up a little bit on these, or we might want to reduce some of the items that we're comparing here. But nonetheless, we get to see some interesting relationships. So look at this one right here where you see we have a really nice cluster. And I opened up this image in a new window so that I can zoom up and we can look a little more closely. But if we take a look, this is Key Bank versus Huntington Bank. And you see almost a perfect correlation on the monthly change across these two. So again, correlated values, we want to think that's helpful when we're looking feature to target. But if it's two different features, we might want to take one of them out because we have a bit of cross correlation here. Now, what we can also see is potential mathematical relationships across some of these. So I'm looking for one that has a bit of an exponential relationship. This one looks a slightly exponential here. The rest kind of just look like a bit of randomness. But if we're looking at two variables and we see that one is exponentially related to the other, and one of these columns is something we're going to use as a feature in regression analysis, then we might want to think, okay, we need to scale this so it's on the same scale. So exponential, you think kind of like a increasing growth in a curve that's going up. We can effectively flatten that down by applying a logarithmic scale to it, and then we're talking in a similar language. So when we're doing our regression analysis, we want to take a look at a map like this and say, okay, what are the items, what are the items where I might want to apply some type of normalization to it, if it's logarithm or something like that, to give us a better linear equation. Now, what about these lines here that you see? They look kind of different, don't they? Well, you'll notice that most of these lines happen where we have the intersection of one ticker with itself. So Apple and Apple gives us this, and then Amazon and Amazon gives us this. And that is a look at the distribution of values for these items. Now remember, we're looking at monthly change here, not closing price total, not the aggregate or cumulative closing price, but instead monthly change. And most of these follow a fairly normal distribution, which actually makes a lot of sense. Because if you think of the stock market, you think about stocks changing a lot over time. Maybe a 15% increase in stock over a year, we would consider pretty good. But month to month, they don't tend to change that much. So most months, we're going to have a change of maybe 1% or 2%, maybe even 3%. And that's all going to fit within the bell of that bell curve. But months where we have a massive change, like a 5%, 10%, 15% change, up or down, those are less common, and those are going to be more on the fringe of that. So this, all in all, looks like really good data to model. I mean, for most of them, given the normalization of their distribution and also given the relationship. But nonetheless, that's why we like to do graphs like this, is to look at that distribution, but also look at the relationship from one column to another and see if we can use one column as a feature, another as a target. Or if we have too many features, we can look at similar columns that are highly correlated and say, okay, maybe we don't need that column. So I hope this video was helpful in talking about how we can look at these plots and how they can be used in regression analysis, and also that's a type of supervised learning, and also non-supervised learning. This will set us up very well for when we actually do a little bit of modeling. I look forward to seeing you then. Thank you.